Welcome back. A little outside the shrine, but nonetheless it's close to the shrine. That's where it is. I picked up this log splitter a while ago. I literally got it for peanuts, and the owner who sold it says that there's an oil leak. I didn't even turn it on, so I plugged it in now and did some tests. Got no idea how it works. I can read the manual, but it's like cheating. So there's a switch here. I'm just gonna press it. The motor comes on, and then right there you can see there's a leak. So the leak is coming from here. There's a switch here, and I'm guessing that is adjusting the direction of travel. So this is the ram, and that's the splitter. So the ram is pushing the wood against the splitter and it's splitting. That's the idea. And if I push this down, obviously it will go back. But if I keep it down, the ram starts going in that direction. But you can see the leak here. So there's oil coming out from right about this area here. So I'll need to take it apart, check it out, look inside and see where that leak is coming from. This is the business end. That's where the wedge is, and that's where the ram works. And down under the ram there is a drain plug right here. So we're gonna remove that and drain the oil first. So this also works as an oil gauge. I was hoping there is going to be more oil in it. I mean, we are talking about 2 ounces maybe that came out so far. Looks like all the oil is drained. So we're gonna go to this side. That's where the motor is. And remove the lever from here and look underneath, because that's where the leak was coming from. 16mm bolt head, and look at that, I got one. Okay, so that's the lever basically, and you can see this is just a nut and bushing that mounts the lever to the stud. So nothing special. So that basically activates this plunger, and the plunger is the one that turns on and off the action, the hydraulic action. So this one is also 16mm. Comes off easy. This was a brand new unit as far as I understood, and it was leaking from the beginning. I'm not sure why they didn't return it. Upon closer inspection, I can see that this stud here is dry, and then the cavity around the stud is dry, and then this one is all wet. So there's a cavity here, and I can shine the light there. I can see that it's wet. There's supposed to be some kind of sealant around it. We're gonna go and remove these studs. These are also 16mm, and I found this socket. I didn't have another 16mm socket. We'll try that one. Just another stud. Looks like there's some copper on the surface here. So these are the two studs. Close inspection, you can see that this is how I removed them. So this is the right side, it's dry, and then the left side has oil on it. So most likely that's where the oil leak came from. I'm gonna go and remove these top ones. Next I'm gonna remove these two bolts. There's one here, one here. These seem to be metric M6 bolts. So there's one on this side, one on that side. So there's definitely some kind of copper gasket there, or copper washer. These are all dry, but this bottom left one definitely has a leak. It's got the shine on it. Okay, the plunger just came out. There's the plunger. A valve. That's what's turning it on and off. Just actuating the flow of the oil. Must be a valve. There's a bolt mounting the motor in the back there. This one, I already removed it, and now I'm in the process of removing these three bolts. I already loosened them up, and that will be holding the motor to this valve body. So if you look, there's a washer and there's some kind of spring washer. These were banned by SAA and ISO 20 years ago. They still use those spring washers. I put two bungee cords to hold the motor. I'm not sure how heavy it's gonna be, but now I'm working on the third bolt here, and I can see this stack separating slowly. So I gotta be careful not to drop the motor. Okay, so the motor is separated now. So there's the motor. You can see that there are two O-rings here, face O-rings. That's what seal the pump. This is the pump housing. It's probably a gear pump. So there's an inlet, an outlet, and a return. And these are just simple O-rings that seal the motor to the valve body. Honestly, my idea when I bought this was to build this into that. If you look, that orange color matches that orange color. So it would be nice to run that 20-ton hydraulic jack with that motor. It would make my life really easy. But maybe I'm just gonna make this work. The cover is off. So these are copper washers under these bolts that were wedging in, and then I managed to remove the cover. This is the cover, and this is the inside. This is where the cylinder mates with the cover, and there's a gland here and a O-ring. And then this section here, you can see this groove, the square groove goes around. It's filled with some kind of sealant. It looks to be like transmission sealant or similar in nature. And that's what seals this cavity from the outside. And this is basically the cavity where the extra oil is being stored. So when the valve opens here through this port, the oil comes in and then presses on the piston here, and that piston basically moves the ram against the wedge. And that's how it splits the wood. The leak came from this bolt here, this bolt hole, and if you look on the other side, there's a crack right here. There's a crack. So I think this housing is cracked through here across, and so that's where the oil is coming out of. Well, better lighting conditions on the altar. I'm gonna go and zoom in on it. So right here you can see the crack, and it completely propagated through and went through this section. If you look carefully, you can see it goes down here, and there's an additional crack down in this area. So that's where the oil from this section is able to escape. If you look from this side right here, you can see a crack going all around. So this entire section is cracked. This might have been due to excessive load or some failure in the casting. Not sure what that is, but you can see right there it's cracked throughout. So next thing, try to get a cover like this. We'll call the manufacturer, see what they say. I called and emailed Yardmax. The lady on the phone took my credit card and shipped me a brand new casting. I only paid for shipping. I asked her for the recommended torque on the fasteners on the cover bolts, but you know, she kept asking which position is it on the assembly drawing, and I'm guessing she was referring to this parts diagram that's in the manual. You can see that each of the parts has a different part number. She was referring to this, but it doesn't have any specification on the tightening torque for these cover bolts. And you know, I kept telling her it's not another part I'm looking for, but a number, a recommendation for a tightening torque. But I never got a response from her. So I went ahead and I looked up recommendation for the M10 bolt. It's an M10 by 1.5 millimeter pitch, and the recommendation was ranging from 40 to 70 Newton meters, which is a pretty wide range. And it depends on the fastener grade, the surface treatment, lubrication, all this stuff. So I went ahead and I crunched some numbers, and this was my calculation. So you can see that we have the bolt head diameter, the hardened washer diameter, the pitch diameter, all kind of geometrical stuff. And then we have the torque at 40, 50 and 60 Newton meters. I just did 3 different options. And then the coefficient of friction both on the thread and the bolt head, I took the same. It's 0.12. So you can get a wide variety of numbers depending on how you change these. I was just looking for pretty much like a ballpark number. And you can see at 40 Newton meters we're gonna get, let's say, 24,000 newtons. At 50, about 30,000, and at 60 Newton meters, about 36,000 newtons. So that's the actual clamp force that is basically acting on a cover in this area, and that's just from one bolt. Next, I took the new cover and I scanned it with my buddy, and here's the scan data. As you can see, this is not a watertight geometry, so it's not suitable for analysis. So I went ahead and I built a 3D model based on the scan, and this is only half a model. I wanted to facilitate mass generation and save on analysis time. I have limited resources at home to run analysis. So I used 50 Newton meters of torque, which is yielded about 30,000 newtons of force, clamp force. Again, this is only the pretension from one bolt. The other load that I need to consider is the actual working load. So when this machine is splitting a log, so when it's force on this ram, then these 4 bolts here are reacting that load. So this log splitter is designed for 5 tons, which is 50,000 newtons. So because that load is reacted by 4 bolts, one is going to carry 1/4 of that, so that's 12,500 newtons. So then the combined load from the bolt pretension and the actual working load is going to be 42,500 newtons. That's what I used in the analysis. So here's the results. You can see the analysis correlates well with the actual failure. The maximum stress is located in the bottom corner of the counterbore, and it is 326 megapascal. Now I consider this is a A380 aluminum, die-cast aluminum, so the ultimate tensile strength for that one per the book is 324. So we are above the ultimate tensile strength. This thing is sort of designed to fail at this load. So on this picture you can see the backside. The red color indicates the maximum stress location. Again, you can see it correlates well with the actual failure location. So I modeled this machine radius at the countersink with a 15 tau or 0.4 millimeter radius, and that's where the highest stress is. So this is the old casting, and you can see the crack right there inside. You can see on this side there's a crack. Before I toss it, I thought I'm gonna do an experiment, and I made this plate, just drilled 2 holes on it. These are M10 by 1.5 bolts, and this will bolt on just like that. I got these spacers, so the spacer is going to retain it the same way the housing retains it on a log splitter, so something like this. Okay, made a couple special washers that are the right size because there's this cavity, so I'm gonna put the washers in like so, and then assemble the nut. So this is the broken side right there. I'm just gonna make this hand tight, finger tight, and then this one I'm gonna torque it until failure, and we're gonna start with 40 Newton meters. So we're gonna start with 40, and then we're just gonna increase by 5 Newton meters and see what is the torque, where it's gonna break. Test to failure, 40 Newton meters. Okay, 40 Newton meters, no failure. Test to 50 Newton meters. No failure. Test 3, 60 Newton meters. Test 4, 70 Newton meters. Test 5, 80 Newton meters. Newton meters, no failure. Going to 90. I had to put wise grips on it, the bolt head was spinning. So, test number 10, 9, 90 Newton meters. Newton meters, no failure. Test 11, 100 Newton meters. Newton meters, no failure. Test 12, 110 Newton meters. That did it. That was about 105 Newton meters. I think the bolt broke. The casting didn't. Looks like the bolt head broke. Here's the bolt. And here's the rest of it. Now I used it for a previous project and there was a center hole drilled in it. And that was probably the weak area. So it promptly broke in that area. Looking at the casting, you can see that there's no failure here on this side. And that was 105 Newton meters. (110 Newton meters). No failure. Got the large breaker bar. Craftsman. Think of a beauty. Just going to break this. I think the casting finally broke. There was no crash, boom, or bang, but I can feel it real squishy. Maybe it's the bolt. Something gave up, that's sure. Well, I'll tell you what happened. This is the knot. It's hard to see a black knot with a dark background, but you can see the threads inside are completely gone. This is the bolt head, and you can see the threads from the bolt head are completely gone. So the bolt gave up and the nut gave up. The threaded connection actually failed, and that was at 110 Newton meters. And looking at the casting, there is no visible marks of failure. It's not cracked on this side, it's not cracked on the bottom, and it's not cracked down here in the countersink. So I think what might happen here is it probably had some kind of porosity that weakened this section. Or it was an overload, but 110 Newton meters, I wasn't able to break that.